Onto oscillations, specifically simple harmonic motion. The definition of simple harmonic motion is that the restoring force is proportional to your displacement, but acting in the opposite direction. You're also going to be producing sinusoidal graphs, whether it's position versus time, velocity versus time, acceleration versus time, kinetic energy versus time, potential energy versus time, momentum versus time. These are all going to be sinusoidal or sine-like. There is also no external force, which means there's no damping happening. If motion starts from the equilibrium point, where F net equals 0, and goes positive, it is a sine function and will behave like this, where x is the x max, our amplitude, times sine, times our angular frequency, multiplied by time. Remember, angular frequency is 2 pi over the period. Taking the derivative of that, that gives us velocity equals omega times x max times cosine omega t. So our V max equals omega times x max. And then A, our acceleration, equals negative omega squared times x max. So our x max, or amplitude of an acceleration versus time graph, is negative omega squared times x max. If it does not start at 0 and go positive, use the correct trig function. Memorize the order of trig functions if you don't have that already. Sine, then cosine, then negative sine, then negative cosine, then sine, then cosine, then negative sine, then negative cosine, and so on. If you start x on cosine, v will be negative sine, and a will be negative cosine. If there's an external or damping force, period will not be affected. Period is the time for one cycle. You might have period for a spring, period for a pendulum, or period for physical pendula. Using the differential equation, you can derive the differential equation shown there. You can derive angular frequency for a spring, square root m over k, angular frequency for a pendulum, square root g over l. If there is no picture, try to think, but the problem mentions simple harmonic motion or oscillation. Think about a mass on a spring, or maybe a pendulum, whatever's more familiar to you. Maybe you want to think about a planet orbiting a star, whichever is appropriate. For instance, if there's a negative potential energy, planet orbiting a star is going to be the right place to go. Your maximum velocity or kinetic energy are going to happen at the equilibrium point for your oscillation. Meanwhile, the maximum potential energy and zero velocity happen at maximum displacement, endpoints where the object changes direction. You can still use Newton's second law here. Net force equals the spring force times mdv, or the net force equals spring force. The net force equals the spring force, which also equals m second derivative of position and time. This is your differential equation, which we talked about solving before.